All right, folks, in this video lesson, what we're going to focus on is the relationship between relations and functions, and then we're going to dive into a little bit more detail on functions. Throughout this first semester, we are going to be looking at different types of what are called functions. So think of the word function, you think of how something works. So it all starts off with to start a relation, or think of relationship, which a relationship usually occurs between two individuals, two things. What we're going to look at in terms of a relation are what are called inputs versus outputs, okay? So a relation is any time we have an input paired with an output. An input, think of those as the things that I'm plugging in, and the output is what I get out of it, okay? Now, in terms of kind of the math approach to this, all inputs we are going to label as X, and outputs we are going to label as Y. All right, so think of a simple relation as, say, maybe a table. Okay, let's say that I have my x's paired with y's. Let's say that I have my inputs of 0, 1, 2, and 3. One way I like to think about this is like a quarter machine. So if I were to plug in, let's say, a dollar bill into a quarter machine, it's going to pump out a certain number of quarters based on what I plug in. So the thing about how a relation relates to a function is that, say I were to plug in $0, so my input is 0, what would I get as my output? Well, my output would be 0. If I don't plug in any money, I'm not going to get any quarters. If I were to plug in $1, my output instead would be 4 quarters. $2 would be 8, $3 would be 12. So that would be considered a relation because we're looking at inputs paired with outputs. Now, in order for relation to become a function, so if a relation actually is a function, we want to know, does that relationship work? To understand if a relationship is a function, normally what we see is there's a pattern, okay? Now, the pattern depends on the type of function, but specifically what makes a relation a function is, does every input have a single output paired with it? Meaning, does every x have one and only one output? Okay, so for example, notice the number 1 for my input is paired with 4. So one input is paired with one output. What would not work is, let's say I had 1 paired up with a 4 and a 5. What that would mean is I plug in $1 into that coin machine and I get either 4 quarters or 5 quarters. Now, every time I plug in $1, I should get 4 quarters. That's how it's supposed to work. If I were to get 5 quarters, that would be nice because I'd get a little extra, but it would not be a working or a functioning machine. So this sort of thing is not good, and this sort of thing is good. So functions should always have a 1-to-1 ratio with inputs to outputs. So in this first example we're going to look at, is a relation actually a function? So again, it's that 1-to-1 ratio. For every input, that input should only have one output, should not be paired with anything else. So notice that I have my inputs here of -2, -1, 0, 1, and 2. So real quick, as I look at these are plotted as points or an ordered pair, that every time I see a point, it's always an x paired with a y, x, y, x, y, x, y. So notice that I have all my inputs. My inputs in this case would be the values in front, so it would be -2, -1, 0, 1, and 2. And then my outputs would be the numbers at the end, 2, 2, 2, 0, and 0. So I want to know, is every input paired with one output? So what does that mean? Well, when I look at it in terms of order pairs, what I want to see is that I don't have any repeating inputs. So notice that my inputs, -2, -1, 0, 1, and 2, do any of those numbers repeat? And here the answer is no, none of them repeat. Okay, now you'll notice that all the outputs repeat, but that's okay. What I'm looking for is that the inputs should not repeat. So since they don't repeat, this one would be a function. If I look at this second example, okay, as you look at the points, you should notice, hey, I got 4, 0, and I got 4, 3. That means the number 4 is paired with 0 and paired with 3. That cannot be true. That cannot work. So this one is not a function. Okay, so in this case, it doesn't matter if I have multiple outputs. What does matter is I cannot have multiple of the same input. Okay, same type of question here, but now looking at a table and a mapping diagram. So in a table, again, I'm going to look at My inputs, notice that I have 0 and 0. I have two inputs. That means the number 0 is paired up with 5 and 6. So that means this one also is not a function. And the last one here is a mapping diagram. The arrows show, what the input is paired with. So -1 is paired with 4, 3 with 15, 11 with 15. Now this one gets a little tricky because you see the two arrows here, that 3 and 11 are both paired with the same output. But what I'm looking for, if this was incorrect, what I'm looking for is this. This right here would not be a function because I have one input paired with multiple outputs. Here again, it's okay to have different inputs paired with the same output. It's kind of like in a car. If I were to ask you, how in a car are you able to come to a stop? Are you able to brake? Well, you could hit the brake pedal. You could hit the emergency brake. You could throw the car in park. You have three different things that have the same outcome of braking. So in this case, this would be a function because each input has only one output. All right, the next thing, once we figure out whether a relation is a function, we're looking at the things we're plugging in and the things that we get out of it, okay? So as a set, the domain is the set of all the inputs, and the range is the set of all the outputs. This is important, especially as we look at functions, because we're going to talk about what are the possibilities of things that I can plug in, and if that's true, what are the possibilities of the things that I can get out. All right, so if you think about the table that I created before with my coin machine, where I had either 0, 1, 2, or $3 bills, and I got either 0, 4, 8, or 12 quarters, right? So this right here would be my domain. I'll label it with a D. This here would be my range. So my domain would be all of my inputs or all of my X values, and my range would be all of my Y values. Now, how does this relate then to functions? So here are two graphs, okay? So what we're going to do is we're going to talk about what are the domain and the range given a graph of a function. So a graph is just a visual way to represent a function. And again, on each graph, you plot points. And the points are given based on the X's and the Y's, right? The coordinate planes that you get. So if I look at, let's say, this graph in A, I have 4 points. 1, 2, 3, and 4. If I were to just list out these points in this first one, I would have the first point is -3, goes left 3, down 2, so -3, -2. Then I would have -1, 0. Then I would have 1, 2, and then lastly I have 3, 4. So those are the 4 points that I have on that graph. So if I want to list out the domain, what I'm going to do is I'm going to list out all the X's. Now notice how this graph compared to B, notice how they're plotted as separate points. This is said to be that the graph is called discrete. You have discrete points, individual points without filling the gap in between. So when I list out the domain for a discrete graph, what I'm going to do is just list out the numbers. I'm going to use a little bracket here, and I'm going to list out all the X's. -3, -1, 1, and 3. When I do this, I always like to write things in numerical order from the negatives to the positives. And I would do the same thing for the range. Again, since we have a discrete graph, we're going to list out the individual range values. So -2, 0, 2, and 4. So I list out all my possible X's and all my possible Y's based on my graph. Now where it's different is in B. Notice B that I have only 2 points listed, and then my graph is kind of connected in between. It's connected with some lines, so I don't see individual points in between. So if that's the case, this is called a continuous graph because from point to point it continues without any gaps in between. So if I look at these 2 points, I have a point here of -2, -1, and I have a point here of 3, 2. So when I list out my domain, it's going to look a little bit different, and the same thing if I were to list out my range, it's going to look different. So the way we're going to write this is actually written as an inequality, okay? So for my domain is a list of all the X values. So I'm going to throw X right here in the middle, okay? Now when I look at my values, okay, my 2 points, I go from -2 to +3. So what I want to do, because this is continuous, is I want to show all the values in between -2 and +3. So since -2 is the low end, I'm going to write -2 on the left side and 3 on the right side. Okay, now since x is between, what I'm going to use is I'm going to use inequality symbols. I'm going to use the less than or equal to. It says here that negative 2 is less than or equal to x, but then x is also less than or equal to less than or equal to 3. This is called a compound inequality you might have learned in Math 1. Okay, so what this is showing, this is just showing that all my inputs would be between negative 2 and 3. And why we write it like this is because it's continuous, which means I can plug in any number between negative 2 and 3. I can plug in a whole number, a decimal, a fraction, anything between those two values. I would do the same thing with the range, but instead of x, I'm going to use y. I'm still going to look at my low value and high value, so negative 1 and 2. I'm going to put my low value on the left side, negative 1, high value on the right side, 2, and then I'm going to fill in those inequality symbols, and here I'm going to use that less than or equal to fill that in, okay? And again, what this shows is that my values, my range values would be anywhere between negative 1 and 2. All right, so that's great. That's beautiful, domain and range, looking at graphs. Now, relating this back to whether a relation is a function. So again, a relation is any sort of set of inputs and outputs. So any sort of domain and range paired together, okay? So how do we know if something is a function or not? A simple way to do this graphically is what's called the vertical line test. So the vertical line test just means that if I were to draw a vertical line anywhere on this graph, that vertical line should hit no more than 1 point on the graph. So it should not ever hit 2 points, okay? And I'll talk about why that is as we go through an example. So I want to know, first of all, if this relation is a function. So if I have here, this is a discrete graph, so notice that I have individual points drawn here. If I were to draw a vertical line through any of those points, vertical line means up and down, will that line intersect at more than 1 point? So for example, if I were to draw a vertical line through this first point, meaning straight up and down, notice it hits that 1 point and that 1 point only. But if I move over to 2, where x is 2, and I draw it there, notice I hit at 2 points. Same thing would happen if I go at 5. I would hit at 2 points. What that means is that the number 2 is paired with both the output of 2 and the output of 5, as shown here. Okay, 2 and 5. Same thing with my x value of 5 is paired with 1, again shown here, and is also paired with the output of 5. So because those two inputs have because those inputs each individually have 2 outputs, this case, this one is not a function. Now the second example, here we have a continuous graph. If I were to draw a line through any value, so again if I did 2, if I did 5, if I did 4, if I did 6, notice I'm always hitting at 1 point, 1 point, 1 point. No matter where I draw a vertical line, always hits at 1 point. So this one would be a function because every input has an output. Okay, 2 is paired with 2. 4 is paired with 3, and so on, just using here my graph to find those values. All right, the last thing we're going to talk about here is now that we understand relations and functions and how to visualize those things with our inputs and outputs, what are some different ways you're going to see this written? So the standard way we write the relationship between input and output, the standard way we would write a function is by using y and x. Again, y always represents the output, x represents the input. So this would be an equation or a formula that shows the relationship between my input and my output. These are what are called function rules. And what it means is that if I were to, for example, give you an input of x equals, let's say, 1, you can take that value of x, plug it into that formula, and it will tell you, based on what that input is, it will tell you that the output would be a certain value. Okay, so for every input, it'll tell you that output. All right, now when we talk more about functions, this is something you're going to see throughout the year. Instead of sometimes writing the output as y, what you're going to see instead is you're going to see this function notation written like this. Okay, it's f parentheses x. Now this does not mean mathematically f times x, but this is f of x. Now what does f of x mean? It means function of x. Okay, so it's just a way of writing, a different way of writing the function rule. But what this thing really represents, again, this is just going to show you what the output is. Okay, so think about this, that y, the output, is the same thing as f of x. Okay, it's just written a little bit different. But as we see this, obviously it gets a little funky. So how does this work? Kind of a simple example here. Let's say that I give you a function of f of x equals negative 4x plus 7. And I want to evaluate this. Evaluate means to plug in. I want to evaluate when x equals 2. So what I'm going to do if x equals 2 is I'm going to take that number 2 and I'm going to plug it in where x goes. So plugging this in, I get negative 4 times 2 plus 7. And all I got to do is simplify that. Negative 4 times 2 is negative 8 plus 7. That would give me negative 1. Okay, so think of this right here as my input, and negative 1 now is my output. Now the way you're going to see this written, though, in terms of function notation, is instead of f of x, right, there's an x right here. I'm going to plug in my input. So my input was 2, and what I got out of it was negative 1. So this right here is my input, and this right here is my output. Very similar to saying instead of f of 2 equals negative 1, it's the same thing as saying 2 comma negative 1. Okay, so there's different ways to write this idea of function, one in terms of function notation, and the other one here in terms of inputs and outputs. All right, I'm going to have you guys pause the video here. Try this next one on your own. So f of x equals 2 times x minus 3. What would you get when x equals negative 1? All right, so you should get negative 5 if you were to plug in negative 1. So again, f of negative 1 equals negative 5. This is my input. That's my output. That is how you would see it as a point. So this is what's, again, called function notation. All right, next example is just kind of understanding that input-output business. So we're going to look at function notation. In this case, we're going to look at the function of the outside temperature after a certain number of hours after 6 a.m. Okay, and I want to know what is the meaning of each of these statements. So here I have this first one, f of 0 equals 58. So understand that 0 represents my input and 58 represents my output. Okay, so t, when we look at this f of t, what do you think t stands for? Now this one's a little bit tough because we have temperature and hours. So in this case, t is going to represent time because we're looking at the temperature after a certain number of hours. Okay, so that temperature is going to depend on the time. So when I see f of 0, what that means is t equals 0. My input is 0. Now what the heck does t equals 0 mean? T equals 0 means 6 a.m. And what that 58 tells me then is that the temperature at 6 a.m. is 58 degrees Fahrenheit. A little chilly. Okay? So we're looking at the input and output. What I would get as my input, what would that be as my output? Okay? If I were to continue on, this one says f of 6 equals 65. So again, what this means is that when t equals 6, what would that be in relation to time? Well, okay, if 0 was 6 a.m., what would be 6? Well, 6 would be 6 hours after 6 a.m. So I'm going to say that's noon, 12 o'clock noon. And that tells me that the temperature there is 65 degrees Fahrenheit. Seems like a nice day, folks. And then this last one, I got f of 3 less than f of 9. What the heck do you think that one means? Well, this one might tell me here that the temperature after 3 hours, so I'll just say the temperature at 9 a.m. is going to be less than the temperature at, well, what's 9 hours past 6 a.m.? That would give you 3 p.m. So here it says the temperature at 9 a.m. would be less than the temperature at 3 p.m., which if you know temperature, that's usually how it goes. The afternoon is usually the warmest part of the day. So again, this is just reading function notation, understanding that relationship between inputs and outputs. All right, last example here. Again, we focus on the idea of inputs and outputs. So in this case, we're going to do it backwards. Okay, so it says given the function f of x equals negative 2x plus 3, determine the input when the output is negative 1. Okay, so what we did before is we took our function negative 2x plus 3 and we took and plugged in for x. So we would take x and plug it in there. But in this case, I'm not giving you x, I'm giving you y. So I want to know what value of x would give me negative 1. So what I'm going to do is I'm going to take this chunk of my function and I'm going to set it equal to negative 1. So essentially what I'm doing is I'm putting negative 1 where the f of x goes. And now my goal is to solve for x. So solving equations, actually get into this a little bit later in our unit, but to solve here, I'd subtract 3 from both sides and get negative 4. Then I would divide both sides by negative 2, and I'll get x equals 2. Okay, so that means my input x would equal 2 to give me an output of negative 1. Now, how do I write this in proper function form? I'm going to say f of 2, my input, would give me negative 1. So again, what goes inside here is always your input, and here's your output. All right, let's have you guys try this last example on your own. I got h of x equals 4x minus 1. What would the input be here when y equals 7? So pause that video, give this one a shot. All right, plugging this in. You got x should equal 2. Again, I kept my function 4x minus 1, set it equal to 7, which is my output. I then solved, got x equals 2. So to write this in proper function notation, f of 2, my function there, oopsie daisies, in this case, sorry folks, it's not f, but in this case it's going to be h of 2 equals, in this case, my output, which was 7. Now notice here I'm not using f, I'm using h. I could use h, I could use different letters. Usually we use the letters based on the type of problem we're talking about. Maybe h is representing the height of something. All right, so in this section, we looked at the relationship between relations and functions, and then went into a little bit more detail on function notation. If you guys got any questions on anything in the video, make sure you jot those things down. Shoot me an email if you need. Otherwise, we'll see you in class.